when I was first in this industry, I was like, humans in space, like I'm focused on the science and building like logistics. I'm not too, humans in space is a whole other logistics nightmare. But what's interesting about this is that I've come around full circle and realized that, hey, uh, that could be the best thing. There's enough people that are interested in going to space or being buried in space. All these different things. But ultimately, what we need is a reason to be up there persistently.
Before we can build a base on the moon, we need something most people overlook: a supply chain. Just like the original Silk Road connected civilizations, the new Silk Road in space will connect Earth, orbit, and the lunar surface through transportation, power, and material infrastructure. This isn't sci-fi, it's the next great logistics challenge, and the companies solving it today are laying the foundation for a sustainable space economy tomorrow. Welcome into another episode of Everything is Logistics, a podcast for the thinkers and afraid. We are proudly presented by SPI Logistics, and I'm your host, Blythe Milligan. I'm happy to welcome in Joe Pawelski. He is the CTO at CisLunar Industries, and we're going to be talking about how to build that new Silk Road in space. So, Joe, welcome to the show.
Pleasure to be here. Thank you.
And just right when we started recording, you had mentioned that you had read The Box, which is a book that's in my background over here. And so that's a perfect jumping off place of where we want to have this conversation, because we've been doing regular space logistics episodes for about a year now. And it's a topic that is not slowing down anytime soon. And I was going through your LinkedIn bio, and I noticed that you have on there that you're a plasma propulsion enthusiast. And I think that that's just the perfect way to kick this conversation off. So how do you become a plasma propulsion enthusiast?
Well, it started out playing a game called Red Alert Command and Conquer years ago, probably in mid-90s. And so this is a strategic game where you try to battle, different folks, and but you win by logistics. So you win by capturing ore and building bases and building a war factory, and you have to have a certain number of things to have the attributes to build the fancier tanks or build them faster and more power plants and all that sort of thing. You could be the former Soviet Union countries in this game, and they had, for base defense, they had Tesla coils. And at the time, I was like, wow, this is really neat. You can zap people with lightning. And I learned quickly that was a real thing. Not the part, it turns out they're actually not very harmful to people. You can shock yourself with it. But I learned all about Tesla coils when I was 13, something like that. I grew up in Richmond. There was a group called the Tesla Builders of Richmond. And this was Richard Hall, who went on to be the first garage fuser builder. So he built a fuser in his garage. And anyway, it turned out that I was hanging out with a bunch of folks from Navy Research Lab and a bunch of other national labs at this age. And they were all into trying to recreate a bunch of the things that Tesla had built. So Tesla coils, but not just that. They gradually got into building fusers and all kinds of really exotic induction drivers and directed energy type devices eventually got into. So that's really what kicked the seed, and that's how I started to meet these people and started to get these mentors that helped me build my own high energy type experiments. And then I started to meet other folks that were similar ages in the community. One of those is Steve Ward. He's got a bunch of YouTube stuff out there, but he invented the dual resonant Tesla coil, which makes music. You guys have probably seen playing AWOL Nation Sail or some other electronic sounds like on the steps of University of Chicago and places like this. A lot of folks have made those at this point. He also invented the quasi-continuous wave Tesla coil. I have one of them over here. I might fire it up here in a second, but it makes lightning bolts that look like swords. I'll show you. Yeah. So this thing right here is a quasi-continuous wave Tesla coil, and makes a little spark when I plug it in, but
whoa,
pretty fun. Yeah, oh yeah. So
that is awesome.
It makes pretty big bolts of lightning here.
Does it hurt?
You can actually shock yourself. We kind of do this as a hobby at CisLunar. We any new hires, they get to play with the Tesla gun, and
there's a little bit of an onboarding that's different.
Exactly. For anyone watching that's seen me at some of the events like Space Symposium, we hosted a party and I was running around with that thing. So So anyway, that's how I got into the whole plasma and lightning sort of thing. It's kind of been a lifelong thing. And so I had this idea probably a decade or two ago, where I was like, wouldn't it be neat if I could get, these folks that I really look up to, that build these things, to all get together and start a company. And I bet we could do all kinds of cool stuff in space with building off of those types of technologies. And sure enough, quickly, so when we started CisLunar, we actually started to build metal foundries in space. And this was to solve the problem of space debris, but also in order for us to build off-world. So, something that I'm really interested. I used to be in heavy industry, building, making plastic bottles and cans at thousands of minutes. So I really wanted to give back and figure out a way to give us abundant resources, abundant energy, but not destroy the Earth in the process. I figured, well, okay, we got to get off the Earth. We got to get this critical mass. But at a certain point, there's a bunch of. I mean, the Earth is made of the same. The Moon is made of the same thing as the Earth. So we have all these resources that we have on the Earth, except the Moon has no biology happening. There's a lot of it's covered in tens of meters of just dust that is metal and oxygen. So like, wow, this is a great resource. So anyway, I started looking into that, and with the NASA project, it was to use metal for metal foundries. So in order to do that, we found out that induction furnaces worked really well. And the folks that an induction furnace for electronics folks works a lot like a Tesla coil circuit. So I ended up hiring some of these folks that I had known from the Tesla building community as some of my first engineers to help build this induction driver. And then eventually we ended up realizing that, hey, one of the cool things about metal foundries, we were looking at, okay, let's start with metal debris. And the problem is getting to the metal debris, because you use propellant to get there. There's this whole Newton's law. It's a real pain in the ass. Rocket equation. You have to get rid of mass in order to move anywhere. Just force equals mass times acceleration. So no matter where you're going, you're burning out of propellant. But force equals mass times acceleration. So rocket fuel can be anything with mass, especially if you're using electric propulsion. I learned about plasma thrusters. I'm like, wow, this is neat. Anything that's that can be conductive, whether it's a gas that you can ionize and make conductive, or just metal, which is already conductive, you can use that as rocket fuel. And I was like, hey, wait a minute. These satellites and things there's 13 most derelict upper stages that if they run into each other, you get the Kessler syndrome, and then you can't launch things for several years. It's like, man, if we could go over there, we could eat these things, we could poop out metal propellant, and we could use that to get to the next thing, and we could use it for station keeping and all kinds of things. So originally, we were focused on this foundry and making this metal propellant, but that introduced us to everyone in the plasma thruster community. And we started to realize that, hey, the very near-term problem is actually logistics. Like, how do you get there just in the first place so that you could use those resources? And we realized that a plasma thruster, one of the hardest things about this is actually building the power supply to operate it. And it got even cooler. We realized that the things that we had been making for our induction furnace and some of the hard problems we've been solving this thing literally, it's like part of it's like a tractor beam. It grabs metal from space that's floating, and then it directs it in with these magnetic coils and everything, and then it feeds into the furnace. And we're like, the plasma thruster folks that we started meeting were like, this part that takes the thing and directs it, and then the circuit that you did that with, that's what we want to learn more about. We think you might have solved some major problems for plasma propulsion. And so I was like, what the heck is plasma propulsion? I got to learn all about it. But essentially, plasma propulsion, it's all these things are similar to what we were doing with Tesla stuff. It's all about, controlling, you have a controlled spark, a controlled discharge, an arc. A lot of times in microelectronics, you don't want arcs. That's what destroys your electronics. You're really trying to prevent that. But if you're doing a plasma thruster or an arc jet or any of these sorts of things, you're trying to create an arc and you're trying to sustain that for a really long time. So it turned out all that experience was exactly what we needed to do. And so that ended up getting us working with all these other research institutions that we work with. Everyone any research institution in the United States that I know of that's doing plasma thrusters, we've been working with in one capacity or another. So anyway, it was like, oh, wow, we can take this stuff and put it on steroids and just do all kinds of wacky stuff with it. So anyway, that's what we've been focusing on a lot, is how do you take something. Now, plasma thrusters are really interesting because you can get much higher specific impulse. And so what that comes down to is, again, Newton's law. You gotta throw mass out. The faster, the harder you throw it, the better. But also, the more massive it is, the better. So electric propulsion allows us to use electromagnets, and basically, the speed of light is a factor that we're up against. But we can accelerate things many times faster than you can with a chemical reaction. Which means that if that number, mass times acceleration, if acceleration is very high, then you can get much more force. And in this case, what ends up happening is you get much better gas mileage, is how you can think of it. They're still working on getting the energy level so that we can get really high thrust. This power is limited in space. It's not the same as a chemical rocket. You burn this, you can get hundreds of megajoules, or billions of watts generated at a time. And right now with solar cells or even a nuclear, you're limited somewhat. But it turns out that we can get very efficient. So it's the way I actually kind of explain it is like the difference between a fighter jet and a train. If you need to get somewhere really fast, you're going to use a fighter jet. But guess what? You're going to have to refuel that thing. Like if you're going to fly a jet from here to somewhere, a fighter jet, especially at Mach 2 or something, you're going to have to refuel that thing all the time. You could take a train and you're going to use a fraction of the gas to get there. And you're going to be able to pool like a whole trainload worth of stuff at the same time. So, so this really gets down to the logistics thing. And hopefully that wasn't too much of a deep dive on propulsion systems. But basically you have chemical propulsion, and you have electric propulsion. And right now, because we can't generate billions of watts on orbit, like that's the equivalent of what like a Falcon 9 is when it lifts off. It's billions of watts generated. So anyway, what we have is we basically have like your air cargo for logistics, and you have your train. And so we have to build those logistics nodes. Anyway, I've been really fascinated by the plasma side. And of course, too, I'm really interested, eventually we can get power levels up to the point where we might be able to get chemical-like thrust. So you might have the best of both worlds, like a fighter jet that can go around the Earth many, many times, or go into space and not run out of fuel, and also have the same kind of thrust. So that's what we're going for. But yeah, I call myself a plasma propulsion enthusiast, because I love all kinds of plasma. And as the folks that build the power supplies, they call them power processing units, we have to understand how all these different systems work at a pretty deep level.
And it sounds like, just based on our previous conversations, that, one of the, I guess when we back it up and talk about sort of space logistics as a whole, one of the bigger game-changing moments was getting that rocket reusability. And now that we have that rocket reusability, where, I live in Florida, and, I've told the story before, but we used to have, maybe a few launches every year. Now there's a few launches every day. And we're talking,
sometimes every day.
And then there's, we had a conversation really recently with Kelly from the Space Foundation, and she's talking about how there's very soon it could be multiple launches every single hour. And so as we're launching more, we're starting to find out these different issues and different problems that we need to be solving. And it sounds like what you're talking about with the plasma propulsion is that that's sort of the fuel for the rockets that needs to be solved as well, and in some of our greater energy problems that exist here on Earth, but will also follow us into space. Did I summarize that okay?
Yeah, so one differentiator I want to make is that right now, because we don't have chemical-like energy levels, so if you could put 1 billion watts into a plasma thruster and have it be the same size as the Falcon 9, you would get chemical-like thrust out of plasma propulsion. But to generate billions of watts, you're talking like a nuclear power plant that's many buildings large. So we don't have that yet. So right now, chemical propulsion is how we get off the Earth. It's the only thing that has enough thrust, to get you. So that's like force over time. So you need a lot of force over a very short time to break free of the drag of the atmosphere. But then once you're out of the atmosphere, now you can use something like electric propulsion to maneuver very efficiently. And if you're operating from the moon, you can actually you can get off the surface of the moon with it's 1/6 of the gravity. So it takes a lot less to get into orbit, the orbital velocity where you're orbiting, and now you can use an electric propulsion system. So what's really interesting about the moon is that the delta, the velocity it takes to get off is actually low enough that like Spin Launch has a launcher that's just a momentum launcher, a kinetic launcher. and it actually has enough velocity. The one that they have in New Mexico has enough velocity, I believe, to get off the surface of the moon. Now it's here on Earth, so it can't launch things off the surface of the Earth here on Earth. But that's kind of interesting because now you could actually launch something without using any chemical propellant. You're just using electricity from converted into kinetic energy, and then you could intercept that with something that's using perhaps electric propulsion that's orbiting the moon, and now you have something that's all EP. We're all, not using your traditional hydrogen and oxygen propellants to maneuver. So right now though we're limited. We have to rely on all of the traditional rocket technology that's been around since Apollo and that era, chemical propellant to get off the surface of the Earth and into LEO. At that point, though, we can do our transfers. So probably what's going to end up happening is that you'll end up having your trains, your trucks, things like that don't need to move super fast, carrying like cargo. You'll also have, of course, like your Falcon 9, your Starships and your New Glens and things that can carry a lot of payload for less, going to nodes. And then you might have kind of your regional jets, regional carriers that go in between might be electric propulsion starting out. So that's kind of where that goes. So for humans, of course, humans probably are going to need chemical prop for quite a while because we need, we're life support every day you're out there. That's another whole cost that you have to think about. But equipment and satellites and all these other things, and again, like moving the propellant to another depot where a human spacecraft might be able to refuel, keeping that in orbit is another really interesting thing because in space, it's a lot like trying to have a boat in the middle of the ocean. If you have a ship in the middle of the ocean, you're not putting an anchor down because it's too deep. There's currents, so you got to rely on your motors to stay in the same position. It's the same thing in space. There aren't currents, but there's other things. There's a little bit of drag if you're near the Earth. You need station keeping, and then if you go further out, there's always gravity from other things that you have to deal with. So EP is very efficient at keeping something. So if you have a gas station or a supply node, that's going to need something to keep it in the same spot, and EP is very good for that.
Yeah, in a very similar vein, one of the episodes that I was listening to prep for this conversation that made a bunch of analogies, and I have it on my little notes here. They said the gateway station is sort of acting as a port or like a lunar outpost. Rockets are essentially the ocean carriers. Landers are the delivery trucks, and rovers/drones are handling the last mile. And then one other piece of that, which you have a ton of experience in, is the manufacturing side of things, and how maybe 3D printers are playing a role. And so to give this audience, sort of those space analogies to the on Earth transportation systems. Some of what the lessons that you've learned, especially from manufacturing, are being taken into space. And I'm curious as to what manufacturing looks like in space. Is it just a bunch of 3D printers? You also mentioned some recycling efforts as well. I think you mentioned the phrase of like taking the machine parts poop and turning that into something that's sustainable. Can you kind of break that down for us?
Sure, absolutely. So, right now in space, manufacturing is more modules. It's like modular architectures, and that's probably what we're going to see first. I've been, in our ecosystems, we talk a lot about modular open source interfaces, but we also talk about making satellites that you could reconfigure in orbit. Because like the propulsion system is a module, the solar array is a module, the comms is several modules. So, something new, some new frequency, some bandwidth that you want to use comes out, you swap out the comms module with a new one, and now you have an upgraded satellite. A new propulsion that's, twice as efficient and uses half as much propellant per delta V or whatever comes along. You swap out that propellant system with a new one. You can. Right now, we have satellites that are designed to deorbit in 5 years. That's requirement if you're in LEO. These are meant to be like disposable, throwaway type things, and that's really, if you think about terrestrial life, like that's how a lot of things are designed. They're fast fashion and everything else. It's not meant to last. Previously, we had designed satellites to last 20 years because they'd be in some orbit where they couldn't deorbit them and out. But of course, designing something to last 20 years, an exquisite satellite, is very expensive. So we have this interesting spot where we're able to make satellites that are like, will last forever. and then we're able to make satellites that are designed to deorbit and fall apart in 5 years. So there's this hybrid in between where you design a satellite to basically just be immortal, because eventually it might not have any of the same DNA. Eventually you replace all the modules and now it's an immortal satellite. And so this gets around the problem of like, I had my first phone was even before flip phones, but it was like, that phone is useless now. You can't upgrade that. There's no way to, you can't refuel it and make it better. It's dead. So you don't want to, you have to be very cautious that you don't design something that is going to just prevent you from innovating. So that's why I think this modular approach is pretty innovative as far as near-term in-space assembly and manufacturing. Is that you might still manufacture these modules on Earth. I'd love to see where we manufacture those modules on the surface of the moon. Having some gravity really helps. There are a lot of concepts for making stations with their own gravity, like big rotating stations, like you've seen in Space Odyssey and newer films. But of course, you still have to get a lot of the materials in orbit, and ISS cost billions of dollars and took decades to build. So you can assume that's the largest, by far the largest ISM project to date is ISS, which is phenomenal learnings from that. And so and also we've done it. We did it with ISS, and it was awesome. The next step is to derive those resources off-world and build something and show that we can build something without relying on research from Earth. But again, I think the first steps are going to be module type satellites. So just like the space station is a pretty good example of a modular approach there. To trusses, all the ways they connected were pretty similar. So now we need to start building satellites that way so they don't deorbit in 5 years. But and you'll probably see this with geo satellites and satellites that are further out, because it makes a lot more sense to do that. And then beyond that, I think you'll start seeing a lunar assembly and manufacturing, where you're still doing the 3D printing and things like that would happen on the surface of something, but then they'd be launched up, because generating power, all those sorts of things, the logistics of how you would manufacture are once you get to the moon, which is not easy, but once you get there, getting things from the surface of the moon back to Leo is actually less energy than getting something from the surface of the Earth to Leo. It's kind of crazy to think of. It's just because the gravity well of the Earth is so big versus the moon. So anyway, there's a very good economic reason to manufacture on the moon, but I that's where I see it going, is that probably 3D printing makes a lot of sense. We've worked with a lot of companies that have developed really cool technologies for 3D printing that could work on the moon today. In fact, one of the things that I just walked past, I'm hoping it ships soon, but it's an extruder that we built for NASA as part of the Artemis program. So the idea is that they'll run an end-to-end demo where they take the dirt on the moon is called regolith, and it's a very fine dusty gray powder, but it contains a bunch of different metals that are oxidized. So you have to take the oxygen out. It's great because right now Starship and all the other types of rockets that can go to the moon, other than the Artemis program, SLS, they have to be refueled to get there. The main thing that they need to refuel with that this makes sense is oxygen, because it has the most mass. So what a convenient thing that once you extract the oxygen from the regolith, you end up with metal as the waste product. So now you have all this metal that you can use to build things. And so anyway, the idea was to take the metal, extrude it into wire, and then 3D print out of this wire. Now, what I expect would be the first things that we would do is to build replacement parts. So they call this ground interfacing tooling in the mining industry, but you can imagine there's going to be a lot of heavy equipment or smaller equipment on the moon. It doesn't weigh as much, but because there's less gravity. But anyway, you're going to be digging through this very abrasive regolith, so you're going to get a lot of wear on those surfaces. And this is heavy metal teeth, like tractor teeth and stuff like that, and wheels and whatnot. So when we did our DARPA work, we identified that the wheels on these rovers, the blades, the things that actually are interacting with this really abrasive regolith, that's what's going to wear out. And that's where, right now it's $1 million a kilogram to get something to the surface of the moon. So like, why would you send a bunch of metal teeth that you could make there if you could just make them there for a marginal cost versus what it costs to make it on Earth and ship it there? Because everything costs $1 million a kilogram. It doesn't matter whether it's water or steel. It's all, the cost of getting it there. So that's where we thought that kind of makes, as far as, beyond the modular approach. Now that, in space manufacturing, if you're launching modules and assembling, and we have that tech today. Northrop Grumman's starting to do stuff with this. Astroscale, like, they're showing that we can actually service, we can remove something, put a new one on. So that's starting to happen today. But where we actually make things in space, that's where I think it's really the larger scale stuff where the economics make sense. It's going to be building things like wheels, like blades. We call it dumb mass, stuff that would be dumb to launch because you can make it pretty easily there. But yeah, like the wire extruder, we made some wire we can make it out of most alloys. 6061 is the most common. So we looked at that for like ISS. Could we take scraps off ISS that are 6061, turn them into wire, and then make new parts? So that's one way to do it. Same thing on the moon. You have silicon is one of the #1 materials. So you have a lot of aluminum. You have a lot of silicon. Aluminum silicon turns out to be a really great wire to use for aluminum 3D printing. So like that makes a lot of sense. You're going to have a lot of aluminum, a lot of silicon. We can make an alloy out of that. We can make it into wire. We can 3D print those metal parts. Steel is another thing that's kind of interesting. We haven't started extruding steel, but there's quite a bit of iron on the moon because, again, the moon is made of the same stuff as Earth. There isn't any carbon on the moon because there's no biological activity. But guess what? All the rovers, half the landers and rovers are made out of carbon fiber. And a lot of the ones that land initially are not going to be reused. So carbon fiber is made out of carbon. And we realized that you only need like less than 1% to make steel. So this is a really interesting, value chain where steel is super useful. You could make full on, all kinds of things if you could make steel and aluminum. So anyway, lunar surface is kind of interesting. But then I think that we would start to build things in space. Gatai is one of the companies that's starting to do some pretty interesting things. So I don't know when we'll actually be 3D printing and manufacturing, wild things in orbit. There's been some demonstrations where they make antennas and, wide aperture arrays, but mostly that's using polymers. There's been years ago, there was this thing called the Grumman Beam Maker, which was meant to go up on Challenger. Of course, we all know what happened there. That got mothballed, unfortunately, but that was it could make beams and trusses that were unlimited, kilometers long. So you could build these big rotating, space, science fiction type stations and things like that. So again, though, it's really kind of are we going to actually end up on the moon in the next few years, like everyone's talking about, or are we going to focus more on space? I hope we do both. And that'll really determine, where follow the money wherever that research goes, or wherever that demand for whether it's military or whatever else drives it. That's where it'll happen first. So now a tangent from here. Interesting panel I was on earlier this week about human spaceflight. When I was first in this industry, I was like, humans in space. Like, I'm focused on the science and building like logistics. I'm not too, humans in space is a whole other logistics nightmare. But what's interesting about this is that I've come around full circle and realized that, hey, that could be the best thing. There's enough people that are interested in going to space or, being buried in space, all these different things. But ultimately what we need is a reason to be up there persistently. That's not just defense. Obviously there's a lot going on with environmental science, a lot with communications and things like that. But we realized from the human spaceflight program before, like, Apollo 13, people kind of lost interest. And all of a sudden there is this drama and everyone's like, whoa, holy cow, like space really matters. Nobody really cares when the Mars rover gets stuck in a ditch. It's, it made a Freaks and Geeks episode at one point, but like beyond that, it's not super exciting news. But when people are involved, all of a sudden there's like a lot of excitement around this. So for me, as someone that's looking at logistics of this, I'm thinking, well, hey, like, you think about like a hotel, and I tell my kids this all the time. When you look at a hotel, how many buildings do you think it takes to support that hotel? How many cars and trucks does it take to resupply that hotel? And you start to realize there's a whole ecosystem built around this one hotel. So, a hotel in space, in Leo even, or, somewhere, in lunar orbit, or who knows, you could put it all kinds of places. all of a sudden, in order to support that, you have all these logistics and these highways that have to be created. And now, as long as somebody's there, you're going to have a constant cycle of resupply in order to do that. So, that's one way that we might end up spurring this type of development, which would lead to really force, if you're just thinking about machines, like 3D printing something on orbit, like you may as well, the time frame isn't really that urgent. So you might just launch it and it's fine to slow boat it. But like if there's people there, now all of a sudden, like, oh, you're leaking. Like, now we gotta fix this like now. And so the urgency of doing that is a lot sooner. So I think there's a lot of merits to that, to helping really get things going and creating. I'd love to see, just like we have highway systems on Earth, something like that in CisLunar space. And for us, CisLunar is the Earth and the Moon. It's the whole Earth-Moon environment. So we're talking about going from Earth to the Moon and everywhere in between, and creating logistics nodes every step of the way, just like the highway system.
Yeah, and what you're saying makes a ton of sense because I think back to Elon Musk said a couple years ago, or maybe even a year ago, that going to the moon was a giant waste of time. We need to be focused on Mars, and we need to go to Mars. But having these different outposts and having these different spots closer to the Earth, it makes a whole heck of a lot of sense in order to get those goals, like what you're saying with refueling, retooling, resupply. It sounds like there's lots of ways besides reusable rockets and a more efficient fueling that needs to take place as well, such as that manufacturing in space. And I always wondered, well, why ignore like the ISS, or why are they just going to, I think they're decommissioning the ISS in a couple of years, and they're just going to send it straight into the ocean. With what you're saying, it sounds like there's a tremendous amount of opportunity that we could save and salvage the ISS into something that's more sustainable and something that is actually useful in space.
Yeah, absolutely. And I've got a ton of respect for Elon. I think we wouldn't be here without SpaceX and Falcon 9 being so successful. I really hope that Starship is equally successful and soon. I think that Elon's, I think, one of these folks that gets laser focused on, he's focused on Mars. We should focus on Mars. But that doesn't be, I think people kind of read between the lines, like, oh, we're going to skip the moon. Well, you can't get to Mars very effectively without the moon. I mean, I haven't had the pleasure of sitting down with Elon and asking him directly about this, but as far as I understand, like, the moon's always been part of this. In order to get Starship to Mars, it's really important that we get oxygen from the moon. So, it's kind of the way I look at it is if we, what's we're good at is like pushing, or we should do whatever we can motivate ourselves to do. If we want to say, let's go to Mars, we're going to learn so much along the way. We're going to end up developing these resupply nodes on, that go to the moon and before we ever get to Mars. And that's going to be huge. Like, we might not even get to Mars in my lifetime. I think we will, but if we didn't, and we just developed all these logistics nodes to the moon on our way there, that would be huge. But anyway, I don't think that Elon's plans to go to Mars preclude the moon. I actually think that they are very much symbiotic. You really need the moon and those logistics to get to Mars, and it's just the way things go. People focus on the other things, and it just gets lost. So.
Well, I think that's the opportunity of what space kind of gives us, is that you can have the folks that are thinking about a lot of different things, and then you have somebody like you that's thinking about, well, maybe we can, reuse some of these things that we've already paid a lot of money to send up, and a lot of time and energy to send up into space. And so I am curious as to, why haven't we started building this infrastructure on the moon yet? It feels like, the last, since the 60s, however much that math is, I can't do math right now. But yeah, it feels like we could have been building there the entire time and already had some of this stuff, this infrastructure set up. So what does that, I guess, what was the reasoning for maybe not building on the moon, and what's changed?
A great, if folks that know me know that I've had a lot to do with ISS and talking about ways we could use it more effectively and continue its life and mission. And I think a lot of that, for the space program, we've had, our best and brightest engineers for decades have created phenomenal amounts of things, and a lot of them have just been put on the shelf. So I fully believe that in the 80s we could have had icing, and then I talk to engineers all the time. They're like, oh, I'm glad you're picking up on, I was working on this 20 years ago. And then you find, I early on, I'd find people that would, and I'd be a little crushed because they'd be like, oh, I had this idea 20 years ago. And they're like, oh man, I guess maybe it's not. And it's like, no, there's some other person 20 years before me. And then I find something where like some guy in Russia wrote about this in the 40s and someone else in like the teens, it's like, what? How did people conceive this thing, 100 years ago? It's crazy to think. But anyway, the ideas have been around. We got close in the 70s, of course, but then, funding changed. I think with ISS too, I've talked to all kinds of levels of folks about ISS and reusing it. And really what I gathered is that, these things are designed for a certain mission. And so far we don't design things in space to have multi-missions. So, for whether it's a satellite, a satellite runs out of fuel, that's the end of its mission, that's the end of its life. ISS, we built it. We proved that we were a superpower and so much better than everyone else in the world. And we were able to collaborate with everyone else in the world and all that soft power. We showed everyone we had soft power. And been there, done that. So now, as far as government's concerned and funding that, it's like, well, we met our objective. The mission was met. Like, it was totally worth it. We did it. So to me, that's the biggest headwind against, that I've learned now. But that being said, I do think that ISS is still a great, there's still plenty of life in ISS and we can use it. One of the things, we talked about recycling ISS. There's concerns to doing that. Like, there's safety concerns. There's also policy concerns, like, how do you get, a lot of it comes down to like, hey, who's going to call Roscosmos and explain to them how we're going to determinate and remove their module? Because, even if we are all good friends and everything else, it's like, well, what if you drop a bolt and it comes back around at orbital velocities and destroys something? Or like, what if you determinate, or you push this off and then it gets, somehow it ends up coming back and hitting us? Or there's all kinds of things that can go horribly wrong, right? And who takes responsibility and ownership for it? Between when you have like all these different nations involved. So really, I think it's a lot more of we call these like policy requirements, or, they're not hard engineering requirements. They're really, diplomatic State Department type things that, someone else that's not me deals with. Now, if you could get beyond that, though, I think that there are, we've talked about using ISS as a propulsion test platform. There's the guy behind Vasimir has proposed this like years ago, and it was going to be very expensive. I talked to a bunch of folks that worked on that program, and I said, hey, what if we were to look at this again and do it when there wasn't any crew on ISS? And it turns out that when you don't have crew on the ISS, it's a lot cheaper to do, it's potentially 1/10 of the cost, because now you're not worried about killing a bunch of people if something goes wrong. But also, what's intriguing about ISS is that it is the largest generator power on orbit right now. There's, I think, over 200,000 watts of power capability on ISS. Now, you can't get all that power at the same time. It's distributed. It depends on where it is. There's, but by far, there's some other satellites that might be in the tens of kilowatts as the next best thing. So like, this is an order of magnitude more than anything that had been on orbit yet. So for somebody like us that's doing a lot of plasma propulsion, we're like, man, there's all these labs that can't, nobody's flown a Hall thruster that's more than a few thousand watts on orbit. So like, what if we could fly a bunch of 10,000 watt thrusters or 100,000 watt thruster or something like that? Like, there aren't vacuum chambers on Earth that can test up to that level, because not for any duration, because generating a vacuum, you're trying to fire a rocket into a vacuum chamber. At a certain point, it's hard to pump that fast once you get to a certain scale. So ISS is really ideal for that. And we've even proposed things like, I've talked to folks at SpaceX, see like, hey, high level, is this crazy? Or like, and they're like, man, we could sell another Falcon 9. That'd be awesome. And like, we could attach it to the deorbit vehicle and like, just got to come up with, $100 million or something, and then we'll be set. But 100 million is 1/10 of a billion. So anyway, the thing is there's things that we could do on ISS, but everything does cost money. I do think though that that's the gambit would it be more effective, more cost effective to use ISS to reconfigure it so it could be used as a test platform for some of these more advanced cargoes, higher power cargoes. More, the other thing that would be obvious is there's companies like SpaceForge that are making chips. They're making very high band gap mediums for chips, which is awesome. But they need to deorbit their vehicle, so like they have the same problem. Having something, a free flyer that's going to have the power level that's easy to use for them is a big gap. So if you could attach to ISS and use ISS's power and then deorbit off of ISS, and then there's companies like Varda, same thing. There's a number of companies that are making these deorbiting vehicles that could be powered through an umbilical on ISS, and then as ISS is deorbiting, all these guys jump off and deorbit themselves. We could run thruster experiments. So anyway, this to me, we've come from, let's reconfigure ISS and send it to a higher orbit, to, hey, let's just use it while it's uncrewed, demonstrate, get the TRL up and prove some of these technologies, de-risk them so that we can actually use a plasma. You could turn a space station into a highly dynamic spacecraft with a big enough, some of these thruster systems we're working on. But until someone actually demonstrates that, it's a big risk to spending the money to do it. So anyway, I think that would be the most effective way.
But it sounds like there's so much more opportunity besides just decommissioning it and just sending it into the ocean. It sounds like there maybe are some conversations that are happening in order to salvage it, to salvage the ISS and keep it in orbit for all of these additional benefits like you just mentioned. Is there a slight chance that maybe that conversation is kind of shifting?
I think it's I don't know. I've been involved in a lot of these conversations at levels that I'm surprised I was able to be involved in. But it's I think that the ship has sailed, figuratively, for ISS being. It will get deorbited at some point. I'm pretty sure of that. I think that there is opportunity to squeeze more out of ISS that is very valuable, that would springboard other innovations. But I think that there's using it for human life support is definitely problematic. A lot of the things are starting to leak. So the safety for human rated things. So to use it and then to push it into a higher orbit, there's a lot of question whether the dynamics of it are it could break apart and cause a bunch of debris, which would be a problem. And just like the way that was built at the time it was built, it's not new space. It's old, very much old space, and most of the folks that built it are retired and doing awesome stuff, doing other stuff. So to find the group of people that would be able to say assuredly that this will be safe, and then there's the whole geopolitical problem that's really kind of the big elephant in the room. So I think that the best thing to do is can we get it would cost 10 different Falcon 9 flights and all this upmass to make free-flying satellites that could do the same thing that ISS could do in the next 5 to 10 years. If we can extend its life a little bit longer, we can get a 10x benefit from it, from these test payloads. And I think ISAM, like rendezvous proximity operations, all the stuff that Northrop Grumman and Astroscale and Starfish and all these guys are doing, like using ISS, especially once it's uncrewed, as your platform for doing, replacing things, proving out ISAM, makes a phenomenal platform for that. So I think that's the best opportunity for it.
Well, keeping in line with that same, I guess, sort of the circular economy. We had briefly talked about this before, but I wanted to dig a little deeper into that aspect, because you mentioned a couple of different interesting things of going to the moon and having mining oxygen and having the byproduct be metal. What other, I guess, methods of a circular economy or circular supply chain of what we talk about here on Earth can be applied into space?
Well, yeah. So again, like getting back to just thinking about the lunar environment there, oxygen to refuel starships makes a ton. I mean, there's companies, Ethos, Starpath, a few others that's their whole business plan. We're gonna land on the moon, we're gonna extract oxygen, and we're gonna launch it back to resupply starships. That's what we're gonna do. So I think that's the most obvious. That one's. Starship is happening, New Glenn is happening. They both need to resupply with oxygen. So I think that's the first step in the circular economy. And then again, like I like I outlaid, like the equipment that converts the lunar dust, moon regolith into oxygen and metal slag. They're going to have wear parts. So that's kind of the first, sustaining those and logistics of keeping those going. So logistics keeping the things that produce the oxygen going, and then the logistics of getting the oxygen to the rockets, and then hydrogen will probably still come from Earth for a while. So that's step one, phase one. And then yeah, I think beyond that, it's going to be trying to get data centers. Probably would be a next pretty obvious resource to use on orbit. Data centers are very quickly, they don't use a ton of energy right now, but as we know with AI and everything else, compute is gonna outpace everything else as energy goes. So there are advantages to doing compute on orbit, especially you have a lot more solar density, so getting energy is good. Cooling is a little bit of a problem, but I'm sure we'll figure that out. So I could see building these data centers, and you start to see some of that in logistics and servicing those data centers, getting those things on orbit, and of course all the comm satellites are going to keep expanding. So that's kind of near term stuff. I think that if we get people on orbit, then that's going to be a total game changer, because now you have to bring cargo and food and all the things for life support. And depending on how adventurous people want to be, that could get really interesting. We could, that becomes a lot more like surface logistics. But the same thing, you're going to have Starship. It's probably going to start out wherever Starship and New Glenn refuel. These will become the nodes that, your ports, if you will, where you're going to get all your new stuff and resupply from that.
No, it sounds super interesting, because from everything that we've discussed, from what my understanding is that CisLunar is kind of dabbling in each one of these different sort of supply chain segments. Is that accurate? Or where, I guess, because it's taken us like 46 minutes at the time of recording to get to what you actually do, what your company does. Can you break down, I guess, what I don't want to say tentacles, but all of the different lines of business that CisLunar is doing.
Well, again, it's a lot like that game I talked about, Red Alert Command and Conquer, where it's like a very, very much of a multi-layer strategy game, where you have to think about, well, we solve this problem, but it's going to open up this other gap. Like so that's, I think that's the way to look at it. So we are very much focused commercially on power management and distribution, and specifically at higher power levels. So 1,000 watts and above is where we start to become very effective. There's somewhat of a proliferation. I mean, it's hardly a terrestrial version of that, but for LEO, low Earth orbit satellites, CubeSats, the CubeSat market is pretty well. There's you can go online and you can get parts for CubeSats pretty easily.
What's a CubeSat?
So that a CubeSat is one unit is the smallest CubeSat typically, and a 1 unit is basically the volume of 1 liter of water, which is 10 centimeters cubed. So 10 centimeters by 10 centimeters by 10 centimeters is 1 U. Happens to be the same thing as 1 liter of water, the way that works out. And typically too, like the density of a CubeSat is similar to the density of water. So a 1 U is maybe around 1 kilogram. 6 U might be 6 kilograms. It all scales from there. So, but anyway, those Aerospace Corporation and a few others, Terran, like these guys kind of really commercialized and made CubeSats pretty accessible. Now CubeSats are not designed to last very long. They go up, they usually don't have their own propulsion systems. Some of the bigger ones might. But they're kind of like a disposable, lowest cost of entry type of satellite. Then once you go beyond that, you get into your microsats and your small sats. Happens to be a small sat conference coming up here in 2 weeks, or a few weeks in Utah. But anyway, so these are anything that's like not like a exquisite type of satellite is typically at this stage is called a small sat. And those get into like maybe 10 U up to like a ESPA, which is just, I forget what ESPA stands for, but it's like a ring. And it used to be, you'd inside the fairing, this ring is what would attach your satellite to the structural part of the rocket. and then the Esper ring usually has a bunch of smaller ports. So there'd be like one big, defense type satellite or weather satellite on the top, and then you might have a bunch of small sats located around it. And then someone was like, man, this Esper ring, we could just use that as the basis for a satellite. So anyway, they're like a meter across, usually, maybe 100 to 500 kilograms is kind of in that range. And so that's where a lot of these satellites for like SDA, the Space Development Agency, the ones that are, they're doing a lot of, communications, also space situation awareness, those are kind of in that class. And right now, most of them are around like 200 watts to maybe 600 watts for their propulsion. Overall, they might, somewhere less than 1,000 watts. The next versions that are coming out, though, are going to be a lot more power than that. So that's what we anticipated, and now we're starting to see that happening. So we've really been focusing on the larger Hall thruster power systems, and then beyond that, just realizing that a power processing unit for a Hall thruster has to manage a bunch of other power sources. It's a power management distribution system, and satellites all we're like, well, hey, it used to be like communications and some of these other payloads would be the biggest power consumer, but now that Space Force and commercial space, they want dynamic maneuver capability. So they want to, it used to be you just get something to orbit. You might use your thruster to get you to that orbit, and then you turn it on occasionally just to keep you in the same spot. Now they want to get to orbit, and then they want to move around and move one place to another and then move back. And so it's dynamic space operations. So now all of a sudden, like your communications hardware, whatever that payload is, your instruments, that's not your biggest power consumer. Now it's your thrusters. So that's an interesting spot. So now it's like, well, if your biggest source is your thruster, then why isn't CisLunar doing our power management? Because the biggest demand is this thing. And we're already managing power at lower power levels for the rest of the satellite. So that's the kind of thing that we started to get into commercially. We've also there's a lot of development on directed energy and power beaming. I stumbled into this concept called dual use directed energy. So the idea there is that you can use energy for like communications. You can use it to power your satellite. So that's pretty interesting, because now you might have a satellite that's 10 kilowatts, but if you can get directed energy over your solar panels, you might be able to get up to 100 kilowatts or something. So get a lot more energy with the same size solar panel, and again with more energy. Now you can move a lot faster, do all that sort of thing. So it turns out that receiving that energy is a similar problem to what we run into with some plasma thrusters, where you got to take energy that comes in one packet and then distribute that at a lesser energy level, or store up a bunch of energy and then send it out in a pulse. So just I jokingly, to put it in layman's term, like we basically build doors and do crowd control for electrons. Sometimes you're trying to empty a stadium really fast. You need a certain type of door for that. That's kind of what a power management system does, or power processing system does, to put in simple terms. So anyway, power management, that's commercially, that's where a lot of our money comes from. But we also do a lot with ISAM still. So we have the extruder that's going to NASA, and we're going to be involved in a new group that's, a lot of the funding for that type of science from NASA is being, I don't think it's being cut. I think it's being moved around. We're not exactly sure where it's going to be moved to. But in the meantime, there's some private groups that we're worth, and also things like Cosmic, and there's a handful of these other groups that they're still keeping the burners on ISAM. So we're still involved in that a lot. And as funding, as we figure out where that's going to be, we very much want to keep pursuing that sort of thing. And then I guess the last thing that we've been involved in a lot is the logistics and interfacing. So we've worked with several of these companies that are looking at refueling and rendezvous proximity operations. A lot of our skill set, is high power electronics and mechatronics. We find that folks that automation type engineers really work well for us. But we developed in one of our first Space Force contracts a way to kind of have cartridges. So it's the idea of having a line replaceable unit as opposed to refueling. You just swap your whole thruster and propellant tank altogether. And we realized doing this we were looking at metal propellant at the time, but we realized that, hey, the thing that holds the metal propellant rods is pretty negligible mass fraction compared to the propellant itself. And a lot of times it erodes, or there's other things that kind of cause it to not be reliable over time. So we kind of want to replace it anyway. So we kind of, the other analogy for this is the propane exchange. So if you've ever been to the grocery store, or if you have propane grill, you swap out the whole tank. You don't have a propane tank. If you live out in the middle of nowhere, you don't have a propane truck come to your house. You bring it to the grocery store, you swap it out in a little cage, and you get a new tank. That's, it's not necessarily new. It's oftentimes a refurbished, but it might have a new valve, so it's not going to leak on you. That's pretty convenient if you're dealing with propane gas. It's a similar thing that we noticed in space. So we've been also focused on, how do we develop, that's the reason I read the box, how do we develop a sea container, if you will, and all the interfaces on a sea container, the mechanical interfaces that allow it to latch to the ship or whatever. How do you build a sea container so that it can fit the most different types of systems? We've been looking at propulsion and energy. So it's like, hey, it turns out that a 6 kilowatt thruster can fit in this box, and so can a 6 kilowatt solar array. Hey, that's pretty convenient. That's a good universal size to maybe start with and start building these. So, and of course, the idea is to build those into modular satellites that I was talking about earlier, the modular open source type of assembly. You can, propulsion systems, power systems, whatever it is, comm systems. And so we've been very, very involved in various capacities on what those interfaces might look like. How do you make them latch right? What's the thermal? And thermal is the big thing in space. How do you move heat? And of course, how do you move power through those interfaces?
Yeah, I mean, everything that you've been talking about in this conversation has felt like building the fundamentals, or everything that we've learned, going back to the box book, all the fundamentals and systematizing certain aspects here on Earth absolutely apply in space. And then one extra bonus to that, I think that you really harp on a lot, and I love this aspect of what we learned in grade school, reduce, reuse, recycle, and being able to reduce some of those costs and recycle some of these goods and reuse some of these goods. I mean, these are all things that we should be thinking about if we could kind of, be able to start our infrastructure and our logistics plan over in a new realm. What does that look like? And so you've done a really great job of breaking that down for us, and how people right now are working on these complex problems. And I thank you so much for your time today. Is there anything else that you feel is important to mention that we haven't already talked about, outside of the fact that I could probably continue this conversation for another few hours?
Oh, I guess I always have to give a plug for NASA and the folks that helped us get here. I do think that at least the small business, the SBIR program, Small Business Innovative Research Program, I mean, we wouldn't be here without that. Getting our legs under us with NASA through our phase 1, phase 2, and phase 2 extension, and then tech flights. The tech flights have really helped. So we've done we've done 3 parabolic flights, and then we have an orbital flight with Momentous that NASA helped pay for. And then we should have an ISS flight actually coming up as well. So all of this, we started out focusing on this metal thing, and that's still happening. And we spun off this commercial product that everyone needs now, which is awesome. So it really did exactly what it was supposed to do as far as we're concerned. I also, Space Force has been phenomenal. I don't know how we didn't have a Space Force all this time. I do think that Space Force is critical, and seeing it grow. We had a number of SBIRs through Space Force, and just the type of folks that we get to work with at Space Force are really awesome. Definitely, some of the leadership there is thinking the same way I'm talking. I mean, a lot of this is from talking to these guys, and just, I describe it like Hogwarts. My job is like Hogwarts. I get to go hang out with all the other magicians and come up with ways to save the world and promote, our an abundant human future. So that's the best thing I can say right now, I guess.
Well, amazing conversation, and I can't wait to do this again because there's plenty of more. I didn't even really look at my notes of what I had, and I probably have at least 40 questions in that document. So that's a testament, of how good this conversation was. So Joe, where can I send folks? Where can I direct them to? Follow you on social media, all that good stuff.
Yeah, absolutely. Well, if you're a power electronics engineer or somebody that's a big builder of Tesla stuff and high energy, we are hiring right now. So please find me on LinkedIn or reach out to our CisLunarIndustries.com is our website. That's the best way to get a hold of us. We are very active on LinkedIn. We are at pretty much every conference. You'll see a CisLunar person. We try to be very accessible. We love to talk to everybody. We're not, I know that I don't know everything. That's probably one of the secrets that I don't mind sharing is that I always ask. I try to find the people that I want to be like, and I surround myself with those people, the people that are really doing it, and that's how you get here, and that's how you keep moving things forward. So, absolutely, if you see me, come talk to me. I'd love to hear it and reach out to us.
Absolutely. I'll put all of that in the show notes. And I echoed that statement. I try to use this podcast to be able to talk to people that are way smarter than me. And you absolutely fit that bill. So thank you so much for joining us and sharing your perspective and helping us, understand more of what's going on in the logistics of space and building that new Silk Road. So thank you again, Joe.
Thank you so much. It's been a pleasure.